very special session as a part of the QIQT 2023. So today we have heard the modern views on quantum chemistry. So we heard a talk on, well, machine learning in quantum chemistry, and then on quantum thermodynamics. And now we will learn how quantum computers can be of use in quantum chemistry. So Professor Sourav Pal is one of the foremost quantum chemists of India. He has made seminal contributions to electronic structure theory, and that is supposed to be the most promising area which can benefit from quantum computers. So he has been an ex-director of IISER Kolkata, and before that of NCL Pune. He has also been in IIT Bombay, and after a very long, illustrious career, he has now become the head of Department of Chemistry in Ashoka University. And he has a long list of awards, including being members of all the National Science Academies, as well as the Commonwealth Chemistry Forum, as well as a member of the Executive Council of the Asia Pacific Society, a J.C. Bose Fellow, well, a Bhatnagar awardee at one point when he was younger. So it's he is one of the foremost names that you have maybe come across many a time. So we will now hear his talk, and over to you, Professor Pal.
Thank you, Sangeeta. Am I audible now?
Yes, it's fine.
Yeah. Okay, great. Thank you. So, yeah, it's a great pleasure speaking in QIQT once more. I think QIQT has become a kind of signature conference now, as quantum information, quantum computers, quantum technology is just beginning to take shape. So, of course, it started in 2021. So I fondly remember when I was the director, and Professor Panigrahi suggested to me that we can have a QIQT workshop at IISER Kolkata. Unfortunately, by then COVID had already come. So we started online, and same trend continued last year. And we are also in the online mode this year. I think online mode has a lot of convenience because people do not have to travel. So I'm very happy that at least through the online mode, we are able to engage more and more people. So I again thank this time IISER Kolkata for inviting me. Of course, I was there as a director for the first two QIQT, but I must thank Professor Panigrahi and Professor Sangeeta Sen for inviting me to deliver this talk. So I was not very sure how I should do, because understanding the audience is different. So every year the audience is different. So obviously I thought that some portions which are important can be repeated. So I must say with that rider, I would start my talk. First of all, of course, as Sangeeta said, I have a very big change in my own professional life. After working in the government for many years, I'm now in a private university, Ashoka University. And it's very challenging here. And particularly in the context of this quantum information workshop, it's very challenging because Ashoka University has a very large ambition to start not just quantum information or quantum computer, but certainly a very big data-centric computer science department. They have a data science department in which quantum computers will play a very important role. So I'm very happy that I moved to a place where there's a lot of emphasis on the quantum computers. I was, of course, at NCL, I was at IIT Bombay, and so on. But I must say that the Ashoka University has put a big challenge, because it's a very different kind of university than you are used to in the government sector. It's a modern university with what is called holistic education. So I'll spend just about a few minutes in Ashoka University. It is, I think, the first liberal arts and university in this country. I must say. Of course, in the US, there are many liberal arts schools, but this is the first in India. Liberal arts actually include science. Unfortunately, there is a lot of confusion about what is liberal arts. So I'm specifically writing that liberal arts and sciences university. But liberal essentially means the students are free to choose whatever coursework, whatever discipline, whatever major, whatever minor they want to do. That is the meaning of liberal. In the normal college setup or school setup, whatever you have done, you have to continue to do it. So if you join as a BSc first year in chemistry or physics, you continue to do chemistry and physics. However, you are condemned. However badly you are struggling and so on. In liberal arts, that is not true. Nobody joins with a baggage. So people choose their credits and eventually they decide what would be their major and minor. So humanities students, for example, can get a major in mathematics if they find mathematics very challenging and they cope up. So I think this is a very short, this thing about what is liberal arts. Chemistry, of course, in Ashoka has been founded in late 2019, almost 2020. So it went through 2 or 3 years of COVID. And only this year, after I have joined here, the chemistry is really kind of coming up. In fact, we have just published a newsletter in which we have a focus on Ashoka chemistry, specifically on Ashoka chemistry in this particular June issue. The major theme, of course, is interdisciplinary research and education. And I think this is very easy to say what is interdisciplinary. All of you know interdisciplinary, but in Ashoka's liberal arts environment, interdisciplinary is such a natural word that I probably need not say it here at all. Undergraduates in minor and major subjects, in different subjects. Very importantly, in the very first year when they join, they have a foundation course, which provide very holistic education. In fact, I have enjoyed teaching a couple of foundation courses in Ashoka. And undergraduate can be 3-year or 4-year. And we are already in line with the National Education Policy. Many of you know NEP, and Ashoka is already in line with NEP. Chemistry department has also started PhD program, and we have a plan to start master's, 2-year master's course as well. So I think our PhD applications are currently going on, and I encourage people to see this. So, of course, I talked about Ashoka University. You can see the students, undergraduate students enjoying life at certain point of time. But the reason you learn in Ashoka is because the education has a very strong emphasis on foundational knowledge, research integrated pedagogy, and hands-on experience with the real world challenges. And that is very, very important. So and many times we actually create very good people, but their hands are somehow tied. We have, of course, in the chemistry department, very small set of faculty. I am, of course, joined as a professor and head of the department. And we have 3 young people who joined in 2020 and 2021, Deepak Asthana, Arya Ghosh, and Munmun Ghosh, organic, inorganic, and physical. And then we have Professor G. Mukesh of ISC Bangalore. Many of you know, is a very eminent inorganic chemist, chemical biology focus of ISC Bangalore as a visiting professor, and Professor Vidya Avsare also from SP College Pune as a visiting professor, and she is likely to join Ashoka as a regular person. And we have also another person who is going to join next week, Sourav Chatterjee from USA. He is going to join us as an organic chemist just next week. So we are slowly building the department, and we'll have about 7 to 8 faculties to start with. We are, of course, since myself is there, and as well as Arya, we have a very strong interest in developing electronic structure theory with a high precision and a motive for right results for the right reasons. And that is a very, very important part that I'm going to highlight, and what challenges does that pose. You have now development of couple cluster based theories. That's what we are doing for resonance and decay, relativistic theories. And we're going to write algorithms and codes out of the theories that will emerge at the Ashoka University. Then we have a lot of interest in energy, environment, and healthcare. As you can see, these applications. And Ashoka, I must say, has just started about a couple of months back, a center for energy transition. And that is a very important center in which we are going to talk of renewable energy mainly, which will also impact environment and partially healthcare. So one of the major challenges will be carbon dioxide reduction, and that is something that we are going to work on. A problem that I started at ICER Kolkata and will of course continue in Ashoka, dinitrogen activation, storage, hydrogen energy storage and its use, and so on. So it will be very interesting to look forward to, particularly in the context of the Center for Energy, which is basically going to include many societal outcomes and of course of industrial use. I must also say at this point a little bit about ICER Kolkata, who is actually organizing this. ICER Kolkata, as all of you know, is an institute of national importance, and I have been deeply connected with the ICER system. I must say that from the time ICER started in 2006, in fact, I was the one who actually started the first common syllabus in Pune when ICER Pune and Kolkata came up, and I was more directly involved with ICER Pune at that point of time because I was in National Chemical Lab Pune. We have set up, this is set up to have integrated research with education, and I find what Ashoka represents in terms of humanities and science, ICER represents within science. That is only different, that we don't have the arts component, but very similar philosophy. And the undergraduate science program is a flagship program. And once again, as I said, interdisciplinary research and education within science here is the focal point. Yeah, I must say this has been outdated in a decade and a half, I should say, at least 15 to 16 years. ICERs have become brand names. There are 7 ICERs, and Kolkata is one of the first 2 ICERs to be set up in 2006 along with Pune. I think ICERs are doing very well, though I have worrying signs for ICERs, which I don't want to spell out here, but I hope ICERs will take care of those worrying signs. Let me first say that either at ICER, at Ashoka, when we are looking at chemistry, we are looking at this quadrant where we not only build our fundamental understanding, but we also look at applications, consideration of use. And this is not very easy because, as you can see, that there are many people who do a very good application, but have not been able to do good fundamental research. On the other hand, there are very good people who have done high research, have not been able to translate. And if you look at our society, we have been weak, I must say, in both, but even more so in the translational research. What we need is, of course, neither here nor here, but we need to be in the pasture quadrant, which is a high science and high applications. So this is what we call it innovation. Invention, discovery, I must say, is building knowledge. Innovation is applying that high knowledge for the society. So in some sense, invention is building knowledge out of nature, and innovation is exactly opposite, building nature or resources out of the knowledge. So I think we need to do this to go to pasture quadrant, and this is a very, very fundamental problem. The problem that we could not go to the particularly translational research has been very nicely captured by C.P. Snow in 1964. It says, we prided ourselves that the science that we are doing could not, in any conceivable circumstances, have any practical use. More firmly, one could make that claim, the more superior one felt. And I think this is a very, very important point that it is trying to say. The ego of the fundamental scientists have always stopped them from doing the translation. And I think this is something that we see in many people at IIT, at ICER. In fact, I have been also at IIT Bombay as a faculty. I had been a student of IIT Kanpur, I must say, in 1972 to 77. So I have seen in all good elite institutions that there has been a lot of resistance in doing translation because of this ego. You could see that more firmly one could make that claim, the more superior one felt. And what is that claim? That my research cannot be used. That's the claim. So you can see this is the real problem that we have. As far as chemistry is concerned, we have separate type of problems. Before I say this, I must say that there's a very famous quotation by Quetelet, that more progress physical sciences make, the more they tend to enter the domain of mathematics, which is the kind of center to which they all converge. You may even judge the degree of perfection to which a science has arrived by the facility with which it may be submitted to calculation. So I'm really coming to the quantum mechanics, that you can do good quantum mechanics, which is a large calculation, you can get knowledge, which is more proper. However, look at this statement in the context of chemistry. And this is a very damaging statement. 2 years after, by Comte, who says every attempt to employ mathematical methods in the study of chemical questions must be considered profoundly irrational and contrary to the spirit of chemistry. If mathematical analysis should ever hold a prominent place in chemistry, which is an aberration, which is happily almost impossible, it would occasion a rapid and widespread degeneration of that science. So it essentially says mathematics has no place in chemistry. And if mathematical analysis should ever hold a prominent place, it will occasion a rapid and widespread degeneration of chemistry. You can imagine these two statements coming within 2 years back to back. And that is a very, very interesting statement in the context of chemistry, in the context of chemical questions. Today, of course, we know that that is not true. There are several interesting chemistry that has been done by which we have shown that the chemistry can be extremely important. I'm sorry about this particular year. It should be 1916, not 2016. So it started with Jean Lewis's theory of valence. I think many of us have forgotten Jean Lewis, who started the octet rule, that there will be 8 electrons in the valence to make an atom stable in a molecule. So, and that is how the rearrangement of electrons in atoms and molecules started. In fact, octet rule was actually given by Erwin Langmuir, though Jean Lewis did almost everything in the octet rule. Jean Lewis was a very interesting scientist by himself. I must spend half a minute on Jean Lewis. He had a very famous book on balance and the structure of atoms and molecules, who defined physical chemistry as encompassing everything that is interesting. I think many of you are probably from the physics background who are attending, but I think you'll appreciate the statement that the physical chemistry is really understanding the physics of chemistry. And it says that everything that is interesting is physical chemistry. I don't want to talk about Jean Lewis, details of Jean Lewis, but he did a lot of work. Also, he talked of separation of and study of deuterium and so on. But one of the great puzzles that he did not get a Nobel Prize. And that, of course, many people know it very well. But he talked of chemical bonds. So the first understanding of chemistry started from Jean Lewis. That why does a chemical bond take place? Why does a chemical bond take place? In fact, this is from Jean Lewis's own handwriting of dot structure, when Lewis started putting electrons in a regular points of a tetrahedron, of a cube, and he could show that if all 8 points are filled up, then it's a very stable structure. Lewis also defined type of bonding, like metal to non-metal is ionic, non-metal to non-metal is covalent, metal to metal is mainly metallic. So in one case, electrons are transferred, electrons are shared, electrons are pulled. Very simple way, but even today, nothing has changed in terms of the proposal of Jean Lewis. Of course, what has changed is that now we are able to quantify. We are able to quantify things using quantum mechanics. And one of the major quantum mechanics that has been done is the solution of the Schrodinger equation. Of course, the Schrodinger equation is written right here, but the time-dependent version of the Schrodinger equation, which is basically the eigenvalue equation of the Hamiltonian, is what is usually solved to get energy in the chemical problems. So which is basically H psi equal to E psi. So that is a very, very important part, which quantifies properties, energy, and all properties which are energy based, including binding energy, including dipole moment, ionization potential, electron affinity, all those are quantified. However, there are another class of methods which have become very popular, which are called molecular mechanics or coarse-grained methods, And these are methods which basically are based on a classical force field. And then you actually apply a very simplistic force as mass into acceleration, molecular dynamics. And that is a very, very important part of the computational chemistry, simply because the systems are become very, very large. And this is the point that I'm going to come, where I emphasize quantum computer. The systems are so large that the quantum mechanics cannot be applied. So quantum mechanics, as you know, is extremely compute intensive. How compute intensive, I'm going to come a little bit later. Then there is a third category of theories, which are purely empirical or statistical theories, like QSAR, quantitative structure activity relationship, which are used in clinical, mainly in clinical and medicinal chemistry. This is not physics based. Whereas in this second category, I would still say it is physics based, except that it's an approximation. And the first category is, of course, more rigorous, but because solution of this Schrodinger equation is technically impossible for more than one electron, we still have to make approximations, but the approximations are of different kind. You can have a different kind of approximations where you can try to look at right results for the right results. Hence, I must say that the computational chemistry has come in a big way to solution of the problems. So I always love to show this triangle of theory, experiment, and computation to give you a solution. And please note that the theory and computation are somewhat different. One is the development of theory, one is application of those theory to computation. So I just put this here. Computational chemistry is a mathematical method which is sufficiently well developed that it can be automated for implementation in computer. And this is where the quantum computers will come. In theoretical chemistry, however, we develop algorithms and computer programs, but that is still theory, but they are not developed to direct application. So that is the essential difference. Modern theoretical chemistry started after G.N. Lewis with a somewhat quantified theories called valence bond theory by Walter Heitler and Fritz London in 1927. In fact, 1 year after the Schrodinger's publication of his quantum mechanics paper. In chemistry, a theory is mathematical or logical explanation of a model connecting laboratory observations to the behavior of the underlying atoms and molecules. So that is very, very important. It must, however, be capable of predicting future observations and is capable of being tested through experiment. But it is not meant only to verify experiments. And that is very, very important. The theoretical chemists are the ones who create means for connecting laboratory observations to molecular behavior. I think this is very, very important, because many times the molecular behavior is something that we do not experimentally observe. We experimentally observe certain quantities, certain data, which have to be connected to molecular behavior, like bond length. We don't directly measure bond length, but we can connect the spectroscopy data to the bond length. And so on. So many examples can be given. So bond length, vibrational frequency, potential energy curve, they are all basically unreal. The real parts are what you observe, the experimental data. But to connect this real and unreal thing, we need theories. And that is where theoretical chemistry is developed. So charge of an atom and molecule is another very, very important property which is requires theory. Activation energy. You don't actually observe activation energy at the transition state, but we can calculate from certain observations. We observe vibrational spacing, but we don't observe dissociation energy. So there is a fitting that has to be done with the vibrational spacing to dissociation energy, and that is theory. So theoretical chemists are basically fitting, bridging this gap. In fact, very interestingly, we are talking of quantum computers here, but before computers came, theoretical chemistry was developed. Of course, in 1927, I told you Heitler in London, there was no computer at that time. I mean, no real computer at that time. There was calculators and so on. Born-Oppenheimer's molecule, Born and Oppenheimer wrote a very, very famous paper in 1927. And Born and Oppenheimer's work, celebrated work, was published even before the computers came. Huckel numbers, all of you read Huckel theory. It was again published before computers came. Huckel published lots of interesting work before the computers came, and so on. If you see up to 1930s and 40s, Bond's theory, Eyring's transition state theory, and of course, Linus Pauling, very famous book, The Nature of Chemical Bond, even that came before 1930s, 1940s. 40s is when I would say computers came in a big way. By 1940s, of course, not in India, but abroad, computers started coming. And probably the first large molecular simulation in a computer was published in 1953, Journal of Chemical Physics. Those who are interested should read this article by Metropolis. It's very famously known as Metropolis algorithm now. Equation of state calculations by fast computing machines. So the computing machines really started. I think the history is very, very important here. Of course, Ruthan's very famous work, which made Hartree-Fock and later on all ab initio theories household work because of the base, knowing how to handle the atomic orbital basis and make it a matrix form. It came in 1951, Reviews of Modern Physics, New Developments in Molecular Orbital Theory, then Dewar and Longwood-Higgins in the Proceedings of Physical Society in 1954, and so on. It continued with Carr and Parinello. In fact, a lot of you know Carr Parinello's very famous work in 1985. And this is extremely important to realize. Martin Karplus, Dynamics of Folded Protein. Today, of course, folding a protein. But I'm going to emphasize this point that folding a protein still cannot be done by quantum mechanics. It uses mostly classical simulation. Chandler transition theory, many of these use quantum mechanics. And eventually, of course, coupled cluster, which has become the gold standard of quantum chemistry, came in chemistry in 1960s, although I must say the coupled cluster existed in nuclear physics in 1950s. And even before that, very similar idea of coupled cluster existed in statistical mechanics by Arcel and Meyer. So coupled cluster, meanwhile, became the gold standard of I should say, chemistry or quantum chemistry. I think this is a very interesting part that we have to understand, that as the computers came, how quantum chemistry developed. So one of the very important work I must today emphasize, and in fact, again, many people forget, is a Hungarian scientist, Peter Pulay. Pulay developed the first gradients, and the gradients are basically, it means how does the energy change with coordinates, maybe atomic coordinates. So the coordinates in a Born-Oppenheimer approximation, the nuclear coordinates, as they change, how does the energy change? And that gives you the gradient, and that is very useful to optimize geometry. So the geometry, concept of getting geometry actually came because of a very easy, fast calculation of the gradient because of Peter Pulay. Meanwhile, Kenichi Fukui, who also got Nobel Prize, did his intrinsic reaction coordinate, very important for the reaction coordinate, in which the chemistry could actually be tracked, how the molecules are moving. Warcel very interestingly developed something called QMMF, and this is a very interesting idea. I've been talking of quantum mechanics and molecular mechanics as a classical thing, but Warcel for the first time started to put quantum mechanics and molecular mechanics in the same system. And very interesting idea was that the most active site will be quantum mechanics and the long-range interactions will be molecular mechanics. So that is the idea of QMMM, which again got a Nobel Prize. It went to a Nobel Prize to Warcel, I think in 2013. Warcel got the Nobel Prize for doing this QMMM. What is interesting is that while all this is happening, we must not forget what Dirac said. A very simplifying statement: the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations much too complicated to be solvable. So you can understand, he talked of a need of a large computer. He said most of it is solved. Although I talked of a lot of theories which happened after, they were basically simplifying the Schrodinger equation. But what Dirac meant is that the Schrodinger equation is in principle able to solve everything, but we don't have big computers. And that is what I'm coming to. That exact application leads to equation much too complicated to be solved. So if you take this view, I say that what cannot computational chemistry deal with? I must first say what is not chemistry. In fact, I must also say that there may be people from biology and physics that, of course, with all due respect to every subject, you can say that what is not chemistry. Everything that we see is chemistry. Then I say, what cannot computational chemistry deal with? In principle, from small molecules to DNA, 3D crystal structure. In fact, a very, very provocative statement is all experiment done in labs can be done in silico. So in silico is basically in computer. We are limited only by supercomputers, not big or fast enough. So you can see that I'm setting the context that we only require big computers to solve the problems. So central theme of the computational chemistry has been to look structure, dynamics, and reactivity, which is very similar to the molecular biology, which has only sequencing and evaluation at the top and the bottom, but they do also do structure, dynamics, function. And I already talked about this particular slide. And we can now calculate by quantum mechanics, good quantum mechanics, energy, dipole moment, orbital energy, and so on, vibrational frequency, reaction pathways, how does the reaction go, energetics, reaction intermediates, transition structure, orbital interactions, shapes of molecules, and so on. What is very interesting is this particular slide. When we are talking of Schrodinger equation in quantum mechanics, this is specifically in connection to the quantum mechanics. How big systems can we deal with? So assuming a typical computing setup, we can have a setup. We can today do a good ab initio calculation. And I will talk about what is ab initio calculation. Ab initio is not one calculation, but there are several grades of ab initio calculation, typically 100 atoms. But the dangerous is here. They are scaling in terms of compute time, goes as n to the 4 to n to the power 7. A very good, very, very accurate couple cluster calculation can take n to the 7, where n is the size of the system. So n to the 7 means if the system becomes double, the computing time becomes 2 to the 7, which is really huge. So you can see that's 128 times, just because the system is doubling. Even the lowest of the ab initio methods, which is n to the 4, is if system doubles, it will become 16 times. Density functional theory is coming up to a very good alternative of quantum methods because it can compete with the n to the power 4 methods of ab initio, but they are much more accurate than such methods. So it includes what is, I will not go into the details, what is called electron correlation, parts of electron correlation, keeping these n to the power 4. Whereas ab initio method, n to the power 4 is a basic method like Hartree-Fock, which does not have any correlation. So DFT, you can go 1,000 atoms. So similarly, Hartree-Fock, you can do 1,000 atoms. When I wrote 100 atoms, remember, I wrote with the n to the 6, n to the 7 methods. Semi-empirical can, which is n cube, can go in the same setup to the 10,000 atoms. Molecular mechanics can do 100,000 atoms. So typically, we're talking of 10 times size n. So this actually tells us that if I, like for example, big protein, where number n is very, very large, I would rather do molecular mechanics because it scales only n squared. But then the problem is if you do molecular mechanics, you lose a lot of quantum information. You lose rigorous information because molecular mechanics is a classicalizing the potential. Same way, if you do DFT, it is reasonable, but it doesn't have the same rigor of a good couple cluster method. So what we really require is ideally for large systems, can we do couple cluster type of method? I'm not saying couple cluster. So can I do protein folding with couple cluster? Today, it's completely out of the dream. It's just say you're absolutely audacious in thinking. So CCSD is where the problem is. CCSD is the gold standard. In fact, I said CCSD bracket T, which is less than N7, but typically N7 scaling. Very accurate, it gives you chemical accuracy, and many difficult problems like excited states, electron attached, potential surface, they all can be done very well. We can do chemistry at a very high accuracy. However, computational limitations force one to make approximations. Either approximations or look at very small systems. One of these two. So it is not an ideal situation. So very typically, I have put a slide on size versus accuracy. As you can see, I mean, this is on the scale. So 1.0 doesn't mean anything. It's just the accuracy, very, very accurate, exact accuracy, 0.1. Then the accuracy scale, as it becomes, this is actually inaccuracy, not accuracy. It is very low. As the error is increasing, you can only do methods. You can go to the large systems by different methods. So with coupled cluster, it's very, very accurate. Non-local density functional theory, you can go larger and so on. Don't worry about the number of atoms. This is not exact numbers, but this is just a scaling. So the idea is the larger the systems, more inaccuracy you built in, more error you built in. This is, please read, this is inaccuracy, it's accuracy chart. So accuracy is building on the upside. So these numbers are actually error numbers. So this is least accurate in the sense. The y-axis is basically accuracy, and this is number. So this is the problem. You today pick your methods, and this is what is called horses for the courses approach. Depending on the course, you pick your horse for the horse course. You know, horse course, those who know horse course, is a very typical proverb, horses for the courses approach. So you pick that and so on. So this is what is actually suggested in this very famous slide. Many of you might have seen this slide already. Yeah, sorry. So you have at a small length scale, which is angstrom length scale, you have ab initio electronic structure theory, which is very, very high quantum mechanics. Then as you go to nanometer, etc., you have molecular dynamics, molecular simulation. Then you have mesoscale simulation, and then Brownian dynamics, lattice dynamics, cellular automata. So you can see as you are going to larger and larger systems, we are changing the methods from quantum mechanics to classical mechanics to even coarse graining. This is called the coarse graining, where the classical simulation simply has atom-atom potential. Here you have a set of atoms, one bead interacting with another bead. And then, of course, you have the engineering length scale, which is, of course, very well developed. Brownian dynamics, lattice Boltzmann, and so on. So this is basically the horses for the courses approach. At least can we use for soft matter biology, which exists somewhere in this length scale, and maybe nanomaterials, quantum mechanics. That is a very, very thoughtful thing, because if you do that, the results that you will get would be extremely accurate. So that is what I have written. Quantum chemistry, quo vadis. Very accurate quantum mechanical methods are very difficult to apply to large systems due to high scaling of computer time. So this is the summary that I have been talking. Lower scaling approximations are being implemented, like fragmentation method, divide and conquer. But even then, they are not desirable because you are making approximations. At the same time, remember, the artificial intelligence and machine learning are being used to simplify solutions. In fact, I understand there's a lecture on machine learning today morning. So that is, of course, simplifying. But yet, let's not forget that they can go to the large system, but in a way which is not physics-based. So physics, this is more of kind of an extrapolation, mathematical tool, but the physics-based quantum mechanics can be rigorously used to obtain reliable and accurate results. The problem is, how do I go to the large systems? So therein lies the scope of a much more powerful computer. And that is the quantum computer that we are talking about. So just very quickly, all of you know quantum computers. I mean, this is a QIQT workshop. I just wanted to bring in the context of quantum chemistry. But very quickly, I should say the quantum information, which is held in the state of a quantum state, two states. And that is very important for the quantum information, that how do I do these classical like bits 0 and 1. I can make combination of 0 and 1 and make several different quantum states, just like superposition of states that you know. So like atomic levels, n and n plus 1, spin states, vertical and horizontal polarization. So many different ways that one can actually build. This is, of course, just 2 bits, but we can have more qubits, like 0, 0, 0, 1, 1, 0, 1, 1. But in quantum mechanics, I can have a linear combination of the 4 states, 0, 0, 0, 1, 1, 0, 1, 1, to generate many more states. And that is the quantum superposition principle. And if you have n qubits, you can keep doing it. This is basically a quantum entanglement problem. Because of the linear combination, you are passing information from one place to another place, A to B. And quantum computer uses very similar phenomena that of quantum information, of superposition and entanglement to perform operations on data. So quantum computers can solve certain problems much faster than the classical computers. And if you can have it, then power is much faster. Quantum computers can simulate much faster than classical computers, and they are reversible. That's very important. They can save energy. So for example, if you take an integer n, just an example problem, find its prime factors. If you do a classical computer, it will take 2 to the power order of ln n to the power 1/3, ln of n cube. Now it's a 2 to the power, you can see that. Whereas if you do a quantum computer, it's simply order of ln n square. Now you can see, even if it is n square n to the 1/3, it has a ln here. So the order is much less. Here the order is 2 to the power. So it can go very, very fast. So I'm just giving example from literature that how does quantum computer solve. If you have unsorted database search, again, classical computer would be order n, quantum computer will be n to the square root n. So I think one can see that one can actually solve the problems in very, very fast. So Feynman had said that the classical computers will require exponential time to simulate many particle problems, whereas quantum computers will require a polynomial time. So that's the difference between exponential and a polynomial time. I mean, it depends on the problem, the degree of polynomial, but it will be certainly much less than the classical computers. However, the problem is more of engineering, that the individual qubits have to be coupled, and then only you can actually go to the large computer. So today, the challenge is to control and couple individual qubits. So that has not been very easy to do. And so you have to run the algorithm with, with less than 10 qubits, and that is not very, very easily done. That what is required, even that is not very easy to do, but people have achieved 10 to 20 qubits. I am not very sure of the current status in the quantum engineering, but what is actually realized that if you want to do a quantum chemistry problem of the kind that I have been talking, with the n to the 6 or n to the 7 algorithm for a very large system, practically to do it, it may require 10,000, 100,000 qubit-based computers, which is, we are far away because of the technology, and that is where technology is very, very important, that we are not able to do many qubit, individual qubit, but it is in principle possible, and probably in times to come, this may be possible that the quantum computers will be able to solve the problems of quantum chemistry, and you may not require, even for protein folding, a classical simulation. I think that is very important to realize. Sorry. So, but the current state, it's still not possible. I don't know if, many of the young people will see that in their lifetime, where quantum computers can actually solve. And then you don't require even AI/ML. You don't require classical simulation. You don't require coarse graining. But that is really kind of the end of the thing. Then all the other theories will go off. What will survive is quantum mechanics and its best approximations. This is, of course, a very, very hopeful scenario from my side. But I can say that, I always say that the problems of quantum mechanics, the problems of quantum chemistry, I should say, in particular, will maybe solved by quantum computers. And we have to see where we go. I think in last few minutes, I don't have time now, 10 minutes maximum, but I want to finish a little bit earlier. I just want to run through what are the work that we have been doing in our group. We are looking at electronic structure of molecule, just to tell you that many of those problems could be solved by a much bigger computer. And to show this, I will rather go to the large applications where we are using density functional theory. Although I have developed a lot of work on couple cluster, we are doing density functional theory simply because these are problems where couple cluster cannot be used. I would have loved to use couple cluster and get much more accurate results. So I will very quickly talk about the couple cluster problems, maybe in a couple of or 2 or 3 slides. We have been developed molecular properties. In fact, I have been doing that from the 80s. A lot of work which has gone into the molecular properties with a different kind of couple cluster. And then we worked on multi-reference couple cluster, equation of motion couple cluster. We recently also started developing low-scale couple cluster. I already talked to the necessity of low scaling. And more recently, in last 15 years or so, we are using complex absorbing potential to the couple cluster to solve resonant and decay problems. So these are called CAP couple cluster. We are able to do very accurate solution of SEP resonance, OJ decay, interatomic Coulombic decay, excited state resonance, and so on. Because these are good bound state methods. But again, we can't apply to very large systems. I must say that in the beginning. More interestingly, you can use more accurate methods by including relativity. And this is where, again, quantum computer will do, because once you do relativistic couple cluster, with the current computing setup, your scope of application becomes even more limited. But within that limitations, we have been able to solve lots of interesting problems. As you can see, in fact, identifying radium, mercury hydride, radium fluoride, many interesting things which will not be identified without relativity. So it's very important that relativity, as all of you know, is very important for the high. So basically, high atomic number. So basically, we are looking at these two in the last 10, 15 years after I have done a lot with the properties, and I call these right results for the right reasons, all highly correlated electronic structure methods where quantum chemistry is very well developed. However, when you come to clusters, functional clusters and materials, like gold cluster, aluminum, they're very good catalysis. And there I am not able to use quantum chemistry of the kind that I have been advocating in terms of coupled clusters. So what do? You use very often density functional theory. If I go to even larger systems like proteins, I told you soft matter, we have to use classical simulation, maybe hopefully QMMM, nothing more than that. So this is where quantum computer can again solve our problem. So we have done a lot of work on gold, aluminum cluster for oxidation catalysis, N2O reduction, hydrogen storage is a very important problem for hydrogen energy. A few interesting results, for example, a hydrogen atom can absorb gold and silver cluster. We have shown that is very potentially active for oxygen activation and CO oxidation. Oxidative addition of carbon iodine bond in aluminum nanocluster, endohedrali doped gold nanocage for efficient oxygen activation and CO oxidation, radical attached aluminum clusters, again, very good for dinitrogen activation. In particular, I must say that we have identified even with DFT aluminum clusters put on a boron nitride doped graphene support. So graphene with BN dope and aluminum cluster, it does a good work on dinitrogen activation. We can also do a lot of interesting work on catalysis, but catalysis design has lots of parameters, and I must say that it requires a lot of interesting work. So one of the things that we have to do, in fact, here I must say that with today's computers, it's very important to use artificial intelligence and machine learning. AI and ML may be able to screen through in the catalysis design, because there are lots of parameters that you have to look at. We are looking particularly at homogeneous catalysis. Of course, I know that for industry application, we need to heterogenize some of this catalyst, but we're looking at particularly pincer complex with less expensive metals for CO2 to formate to formic acid. We have been able to achieve this today in a very important project of the government project, SCRB imprint project, which was actually run from ISA Kolkata. And what we are now trying to achieve is CO2 to methanol. You can see very important And you can do good quantum mechanics to do that. And that's very, very important. However, metal clusters are also very interesting. In fact, one of the interesting metal cluster is AU8, which is inert, but if you dope one gold by silicon, it becomes catalytically active. And this is a very interesting part of the cluster. Cluster is not bulk, it's a very small number of atoms. So if you change one atom, lots of things start changing. So pristine gold cage. Again, if you put a metal inside AU18 itself is not very active, but if you put a metal inside, it becomes very, very active. I already talked of the aluminum cluster. So for example, one example I can give for AU18. This is of course just AU18 with CO oxidation, CO2. You can see the barriers. We have done a complete reaction mechanism. Transition states are two transition state 0.7, 0.45. And then if you see the putting the metal, how does the transition activation barrier drop down? So now it becomes catalytically more active. The barriers are low. You have just put AU18 with sodium, magnesium, potassium, and calcium. I must say that these catalysts are today possible to synthesize. So they are no longer just fictitious catalysts. You can actually have AU18, and people have synthesized metal doping in a gas phase. So most of our theories are very relevant. And I talked of the hydrogen chemisorption. You can see if you took AU6 and AU8, again a CO oxidation reaction has a very high activation barrier. But as soon as you put hydrogen chemisorb, the barrier drops down to almost nothing for AU6 and significantly less for AU8. So AU6H is a very good catalyst for CO2 activation. It's also shown in this binding energy and the oxygen-oxygen bond length, which is also stretched. So it has it can activate the oxygen molecule. I would not talk much about it, but I just want to say that very recently we are also applying DFT for anode materials in lithium-ion batteries. Lots of interesting materials we are looking at, in particular blue phosphorine, then graphene. Blue phosphorine as an effect of dopant and lithium sodium absorbed, MOS2, tungsten sulfide, some of these with heterostructure with graphene. So very interesting materials that we are looking at for battery material. I'm pretty sure batteries are going to become very, very important. Let me end my lecture with an outlook that you essentially need to apply quantum mechanics, the fundamental insight from atom and molecule to nano and bulk. So you require to develop theoretical methods at a different length scale. And that's what we have been trying to do. So the path forward is to have accurate methods for large system. And this is what I have been emphasizing. We have approaches, approximation approach, fragmentation, and also, as I said, multi-scale simulation. However, ideal would be to have very powerful computer. That could be an alternative. Strong correlation in molecules and solids. So grafting of AI and ML. So what is really required is a combination of these. Not only you need a good accurate methods, you need to graft AI and ML properly, you need a good computer. And then we should be able to solve most of the problems at a reliable accuracy. We don't need computer for a problem where you don't require, please understand. But there are cases where even approximate methods cannot be applied. Even good approximations cannot be applied. You have to make really bad approximations, which is not reliable. So I'm talking of advocating quantum computers for such problems where you require good results. So these are the challenges of quantum chemistry. I must say improvement of DFT. I did not talk of DFT, but DFT reliability depends largely on the functional that you use. Improvement in band structure, optical properties, conductivity in the material, complex system and soft matter, as I said, using multi-scale simulation, strongly correlated system, non-adiabatic molecular dynamics. I didn't talk about it, but this is a very, very important problem where it requires very large computer. I hope somebody is speaking on that, but non-adiabatic molecular dynamics also require very large computers. Highly correlated quantum chemistry methods to large systems, then identification of molecules for drug design, new functional materials, storage. These are all application challenge. And of course, AI and ML in coding and functional use. So one has to realize, of course, scope of each of them, that there is a limitation and one should actually work within this limitation. And that will make us go from fundamental science to computing science to generation of technology. And I believe quantum technology is the right word, because eventually quantum mechanics is a fundamental science. Through a computing science, which is quantum computer, we can generate quantum technology. And that is why it's very, very interesting, this particular conference, that you have quantum mechanics, to compute science to technology. And today, technology, to generate technology, you really require reliable results for large systems. So it is going to be possible with the highly efficient computer codes. Of course, codes are very, very important, but today codes are almost getting saturated, I must say, in terms of algorithms. So we really require some other breakthroughs. I've just put down some of the challenges. I mean, there are more in the basket that you can think of. With this, I think my time is anyway up. Let me thank all of you for your attention, and I acknowledge materials from different sources. I must, of course, though it's not in the slide, I must acknowledge for the work that I presented from my group, various students. It's very hard to give the names of all the students, but I acknowledge many, many of my students from National Chemical Lab, Pune, IIT Bombay to IISER Kolkata, and even now from Ashoka. So I think I must have graduated more than about 45 PhD students. So it's very hard to give names of everybody, but many of them figure in all the work that I presented from my group. And of course, funding from various sources, I must say CRB, DST, Indo-French Center, 2 projects from Indo-French Center, DST, DARD projects, and several other projects of exchange projects from various different countries, projects from a very important computing center for development of advanced computing. In very early days, I used to work with CDAC for developing Hartree-Fock program on parallel machines at that time. So I must also thank CDAC for kind of supporting and sponsoring my project. So various funding agencies at different times, CSIR, of course, being in National Chemical Laboratory, has been one, BRNS, Board of Research in Nuclear Science. So many, many funding agencies which have supported. And of course, all the institutions where I worked, NCL, IIT Bombay, IISER Kolkata, for all the support they provided. And I hope this will continue in Ashoka as well. Thank you very much.
Thank you, Professor Pal, for a very wide and interesting talk. So the floor is open for maybe 1 or 2 questions, if there are any.
Can I ask one question?
Yes, please.
Please.
Thank you for your talk. You mentioned about quantum computers. So could you please name the quantum algorithms which can be used to solve some specific problems of quantum chemistry?
Yeah, so I already talked about lots of problems of quantum chemistry. So for example, if you want to even design a catalyst, you understand? So with the catalyst that I was talking of is the transition metal catalyst, where you have a metal and a large organic ligands. Or if you want a material for hydrogen energy storage, which is again organic metal plus ligand, which are very, very large. So today we have to use very crash quantum mechanics method like DFT at a low functional level, right? So if you want to do, let's say, couple cluster for such problems, which are n to the 7, today it is simply not possible. So most of the materials problems that I showed are all done by DFT. As I mentioned, most of them are not possible to do with a highly accurate method. No, forget about couple cluster, even MP2, which is n to the 5. It's not really possible today. And those are the problems where quantum computers can solve effortlessly. If you have good computer. Today, of course, such a quantum computer still does not exist. Okay, so the problems are plenty, in fact. You want to do a small protein folding, use computers, use at least QMMM method, you require big computers. Today, it is not possible. So I can tell you how many problems today are not possible. You want to apply or you want to study drug membrane interaction, which is a very important part of biology. How do you do it? You do coarse graining. Not even classical atomistic simulation. You do coarse graining, where group of atoms form a bead, you take a classical potential. All of you know that that's not correct. That's not accurate, right? The approximation works reasonably well, and we are happy with that. So many problems, there are more problems which can be solved now than what are being solved today. So there are many unsolved problems today, which actually can be solved by quantum.
Thank you.
You want to get a very good potential energy surface of a large inorganic molecule. You can't do that today. And that's very important for transition metal chemists, right? So I can keep quoting. You just look at inorganic chemistry text. There's so many organic molecules, big organic molecules. You can't do. People are only using DFT, sometimes not even that, molecular mechanics. So all those will require quantum computers. Is it clear?
Yes, it is clear. Thank you.
Okay, so we thank Professor Pal once again. So we do have a talk after this, but it is not in the realm of quantum chemistry, but please feel free to continue. It's by Professor Ivan Sapkovic, I believe. Okay.
Yeah, I'll be taking over.
Yes, okay.
Yeah. So our next speaker, researcher in University of Geneva,